In this video, we introduce the concept of dipole moments in molecules. In homonuclear diatomic molecules, the distribution of electrons is symmetric around the molecule. For example, in a hydrogen molecule, oxygen, or fluorine molecules, we can draw a shaded region around each molecule to indicate where we have the highest probability of finding electrons, say 95%, and these regions are symmetric around the molecule. In heteronuclear diatomic molecules instead, the electron distribution is uneven and more centered around the more electronegative atom. In the case of hydrogen fluoride, for example, there's a higher distribution of electrons around the fluorine atom, and we indicate this with a delta minus around the fluorine and a delta plus around the hydrogen. Similarly, with nitrogen oxide, there's slightly more electrons around the oxygen, and we indicate this with a slightly uneven electron cloud. When a molecule has a negative end and a positive end, it is said to be polar, and it's the same can be said about bonds between unlike atoms. Polar bonds can occur both in diatomic molecules and larger polyatomic molecules. A polar molecule can be viewed as a dipole. Each partial charge, delta minus and delta plus, are placed in the molecule at a distance that we'll call d. And so we define the dipole moment mu as the product of this partial charge q multiplied by the distance between the two. Dipole moments are indicated by vectors, which can also be seen as arrows, and they point in the direction of the negative charge. The start of the arrow is often indicated with a cross line, which symbolizes the symbol plus. We know that polar molecules have a dipole moment because they align when we place them in an applied electric field. When a molecule is formed by two unlike atoms, then its dipole moment will be larger the larger the difference in electronegativity between the two atoms. For example, if we compare Hi to HBr, in Hi the difference between electronegativity of H and iodine is 0.4, and that determines the dipole moment and the polarity of that bond. For HBr, the difference in electronegativity is 0.7, and that leads to a larger, almost double, dipole moment for HBr than for Hi. The same thing can be seen for HCl, which has a larger difference in electronegativity between H and Cl, and therefore an overall larger dipole moment. The dipole moments of triatomic molecules can be obtained by using the sum of vectors. For example, in ammonia, by summing the three vectors that correspond to the three NH bonds, gives us the overall net dipole moment of the molecule, which is quite large, 1.47 dBi, and pointing upwards in this figure. In the case of chloromethane, we also have a large dipole moment, and it also points upward in this figure because the carbon is much less electronegative than chloride, and also each hydrogen is much less electronegative than the carbon. So mostly, molecules containing polar bonds have a net dipole, but sometimes the sum of all the dipolar bonds cancel out. This is the case, for example, of carbon dioxide. Although each carbon-oxygen bond is polar, the two bond dipoles are equal and pointing in opposite directions, and so this molecule has no net dipole. The electron density distribution is symmetrical around the central carbon. Similarly, for tetrachloromethane, the dipole moment is zero because all the four dipoles of the CCl bond are symmetrically arranged in a tetrahedral geometry. It is important to know about molecular polarity because the interaction between molecular dipoles determine many physical properties of condensed phases, such as boiling points of liquids. You must be able to recognize the polarity of a molecule based on the VSEPR structure. For example, in the molecule SF4, which takes on a seesaw shape, we have a dipole. On the other hand, the molecule CF4 has no dipole because it is symmetric around the carbon and all the dipoles of the CF bonds cancels out. And similarly, the square planar geometry, all the polar bond cancels out and there is no dipole moment.